So this is joint work with Meven Lennon-Bertrand that you can find in this room, and Nicolas Tabareau and Âric Tanter once again. So I already had a really nice introduction to the topic of dependent gradual types, but let me try to pitch it my own way another time. So my goal in this talk is to try to build a dependently typed proof assistant which is easier to use. So I will use the same example of fixed size list, this time called vectors, which take an argument, a base type A, and specification of a size of a list that is given by a natural number. We have two kinds of vectors, the empty vectors that have size 0, and the counts of a head on top of a tail of size n, which is of size successor of n. On such vectors, we might want to define various kinds of functions, such as map or filter function. A filter function is a function that will take a Boolean predicate on the element contained in the vector, a vector of some length n, and that will try to filter the vector by this predicate. How do we do that? In the case of the empty vector, we just return the empty vector directly. And if we have a head on top of a tail, then we check whether the Boolean predicate holds of the head and either recurs on the tail or keep the head on top of the recursion on the tail. This function filter takes an argument of size, whose size we know statically, given by len, but what's the size of a result of filtering this list by an arbitrary predicate? Well, at first, we cannot give a closed formula immediately. We have to think a bit about, how does it compute? And actually, the problem for computing the size of a result is that this size of a result depends on the dynamic value of the list that we get as input. So in order to prototype efficiently in a dependently typed language, we might want to say, okay, for now, I will just put some unknown value that I will write question mark, and I will try to evaluate my program and see how it works. Let's see how things unfold. So one thing that we have to consider as implementers of a dependently typed language and a proof assistant is that adding this kind of question mark creates some kind of troubles in the type checking procedure. For example, here I have something which should be of size vector of size 1 plus some unknown term, and I want it to be of size vector of unknown. So I need to be able to optimistically assume that these two things are consistent. So that's the kind of thing that a gradually dependent typed proof assistant should be able to provide you. Now, on such an example, how do we run actually the thing? Let's try to see the example like filtering two different lists. In the first case, I'm filtering the list 1, 2, 4 by the predicate even. And in the second case, I'm filtering the empty list. In both cases, we can evaluate the results of filtering this list. And here I can, both cases type check because we have results that are of type vector of unknown length, which is consistent with the successor of length, so that we can apply the head function. So reducing the filter function gives us, in the first case, head applied to the list which contain only 2. And in the second case, we obtain only the nil list. Now, in the first case, we can further reduce the head on the list that contains only 2 and get a result that will be 2. In the second case, however, we have a nil constructor, which is supposed to be in a type successor of some unknown type. And this should be incompatible with the fact that things in a successor, vectors of a successor size should be of a head on top of a tail. And so we need to enrich our language with errors to handle this kind of impossible case that happens dynamically. And so here I will get an error. For prototyping purpose, I could also say, okay, but this second case where I'm passing nil is not useful So I might want to give a simple specification that refines this unknown bound. For example, saying if my input list is nil, then the resulting size will be 0, and otherwise I will over-approximate, saying that the resulting size is unknown. In such a case, the second example, where we try to take the head of filtering an empty list, will not type check anymore, so we'll have gained a bit of static information on which programs type check. And so that's the motivation for using gradual dependent types for prototyping purpose. So how do we achieve such a gradual dependently typed language? Well, we proposed in previous work to separate this language in two sub-languages, a first surface language, which is actually gradual, and a second language, which is a cast calculus. And the gradual language elaborates to the cast calculus, while the cast calculus provides the computational meaning for the gradual language. The cast calculus contains unknown terms and types. Every type is inhabited by unknown terms. Every type is also inhabited by error terms, and we have arbitrary cast between pairs of types. In order to control this cast, a notion of precision between types gives us the information about how precise the information, the type that we have is. So the most precise types are the static types, while where we lose precision, we get to the unknown type, which is actually maximal for the precision order. Precision between types control cast by enforcing that casts are valid in the following sense, meaning that if two types, if A is more precise than B, then casting from A to B is an injection, and it has a retract, which is a cast from B to A. And the fact that we can interpret the notion of precision as such embedding projection pair will be the fundamental semantic criterion to build all our language. So now, in previous work, we also observed that actually trying to get all properties that we want from such a gradual dependently typed language is not possible. We cannot have at the same time the gradual guarantees that we want, a normalizing language, and conservativity over the base language that we try to gradualize. And in order to have a proof assistant, normalization cannot be traded. We want to have normalization to ensure that we can actually have a decidable type checking algorithm and that we can actually implement our proof assistant. Moreover, we cannot trade the embedding of the base calculus because we want to be able to reuse all programs from the existing literature, from existing code programs. So in this work, we had 3 different variants in previous work that were trading the different possibilities. And in this work, I will concentrate on this variant, which has both an embedding of CIC and that is normalizing. So now I will look at the cast calculus, which has this property. So I have this cast CIC n, which is both normalizing and conservative over CIC. However, it is not globally, it is how far it belongs to show some gradual properties. And how do we do that? Well, we'll actually internalize the notion of precision inside the type theory so that we can actually reason inside the type theory on the precision between types. So we call GRIP the resulting type theory, which extends this cast calculus with a notion of precision, actually 2 families of precision, one for precision between types and a family for precision between terms. And these types of precision are actually propositions that inhabit a pure universe of proposition, prop. And this universe of proposition is pure in the sense that it contains no errors, no cast, and no unknown terms, which make it a good place to have sound reasoning for the type theory. So what does this internal notion of precision actually mean? Well, we can explain what it means in terms of a dynamic gradual guarantee. So a dynamic gradual guarantee is saying that if I have a term x which is more precise than a term y, and a context for values in type A, applying the context to x should be more precise than applying the context to y at Boolean types. And we have that the dynamic gradual guarantee will hold for a context C if and only if this context is related by precision inside the language at type of Boolean predicate on A, and if and only if this context is monotone. In order to understand concretely what this formula actually means, we should look at precision on Boolean types, which contain true and false as usual, but also the exceptional values provided by the gradual language, errors and unknown. And we have a lattice where error is the smallest element and unknown the biggest one, meaning that the dynamic gradual guarantee actually means some kind of error approximation. Meaning that if my value x plugged in the context C does not error, then I'm sure that the value y plugged in the context C will not error either. So now that we have some understanding of this notion of precision, how do we prove actually in our language, how do we derive a proof of precision? Well, let's have a look at two terms. The first term is a function from natural to natural that add 1 to a natural number. And the second one takes an unknown, a term of an unknown type and cast this element to natural numbers and then add 1. If we are able to prove that the first static term is more precise than the add unknown function, then this will mean that add unknown will not have errors on good input. And how do we do such a derivation? Well, we start from the judgment that we want to prove. Now we look at the precision at function types, and at function types, precision is actually extensional. It maps elements related by precision to elements related by precision. Now we will intro the argument in the context and do some computation to unfold the add 1 and add unknown. And we need to compare two application of +1 of successor. And successor is actually monotonic. So we can actually just forget about it and show it's enough to show that x is more precise than the cast. Finally, to complete this proof, it's enough to know that whenever we have two types that are related by precision, the embedding projection properties will allow us to get that this cast is actually a right adjoint, so that we can use directly the proof that x is more precise than z at the type not more precise than unknown. So now, this proof that I just gave is made out of some principles that we have on precision, such as transitivity, quasi-reflexivity, the adjunction properties that I just used that are coming from embedding projection pair, and also an important property that allows us to characterize precision between types that are not directly related by precision. On the other hand, we cannot have everything in our language. In particular, the precision on types is not the same thing as the precision on the universe of types. And we have, this allows us to keep a normalizing language, but it makes reasoning a bit surprising, let's say, and we have to use some explicit cumulativity in order to regain enough expressivity in our language. So really quickly, I would like to outline that we have some interesting meta-theoretical property on this language. It is normalizing, it is consistent, normalizing, and moreover, we can carve out some fragment of this language where we can automatically derive that terms are gradual. So to conclude, we have a proof of concept of this type theory in AGDA. And we have a model in Coq that validates the meta theory that I just alluded to. We have non-gradual operations in this language. So for example, we have a catch operation on inductive type that I didn't have time to talk much about. And this paper can also be seen as a way to address the question of catch in a gradual world. And we add precision internally in order to reason post hoc on the gradual terms of this language. So for future work, we would like to have elaboration from a gradual source. Right now, we are working only with a cast calculus. And we would like to have more general inductive type, maybe an actual implementation from this source language, but this will have to wait for another time. Thank you.